Okay, so first we need to know what is thermal capacity. This part involves calculation and formula. Okay, now let's see the first point here. The thermal capacity of an object is the amount of heat energy required to raise the temperature of that object by 1 degree Celsius. Okay, so that is the definitions for thermal capacity. Raise an object by 1 degree Celsius. What objects or how big is the objects that we can use? Should we use small object or big object? It doesn't really matter, man. Any object, you raise it by 1 degree Celsius, then the amount of heat required is known as the thermal capacity. Okay, so because of this, right, you should think of the unit of thermal capacity. Amount of heat energy, this is joule, required to raise the temperature of the object by 1 degree Celsius. So degree Celsius. So the thermal capacity, right, is hence having the unit of joule per degree Celsius. Per degree Celsius, thermal capacity. The unit of thermal capacity. Okay, now, okay, the greater the thermal capacity of an object, the more heat energy it takes to raise its temperature. So different objects, we have different thermal capacity. Even the same substance of different size, we have different thermal capacity also. For example, 2 kg copper and 1 kg copper, they have different thermal capacity. The 2 kg copper has a greater thermal capacity, the 1 kg copper has a smaller thermal capacity. So that is the thing. Okay, different objects have different capacity. Object of the same substance but different size, different mass, it has different thermal capacity also. Okay, so the thermal capacity is also equal to the amount of heat energy an object will give out when it cools by 1 degree Celsius. So this is the opposite situation. That means if you heat up the object by 1 degree Celsius, the amount of heat energy absorbed is the thermal capacity. But in the other way around, when you cool it down by 1 degree Celsius, the object will release this amount of heat energy. Okay, so thermal capacity can be used in two ways. Either to know how much energy is absorbed during heating of the object by 1 degree Celsius, or how much heat energy is released during the cooling of the object by 1 degree Celsius. So used in two ways. Now the next point, the energy E required to raise the temperature of an object by an amount T is given by the equation. And now we have the formula. E equal to thermal capacity times T. Okay, times T. So this is the formula. And from this formula, the unit makes sense. As you can see, if I rearrange this formula, thermal capacity equal to E over T. E is energy, unit is joule, temperature, degree Celsius or Kelvin. Degree Celsius or Kelvin is up to you. So at the end, it becomes joule per degree Celsius. So that's why the unit makes sense here. Okay, now let's see the relationship between thermal capacity and specific heat capacity. Okay, so we have two different terms here. Both have capacity, but this is thermal capacity and this is specific heat capacity. So the thermal capacity of an object is related to the specific heat capacity. There's a relationship. Okay, so but the relationship is given later. Now they give us an equation. They give us the equations to relate thermal capacity, and the C here is the specific heat capacity. So you take specific heat capacity, multiply with the mass, then you get thermal capacity. That is how they relate. Okay, how they relate. Specific heat capacity multiply with mass, then you get thermal capacity. So of course we need to know what is specific heat capacity also. So let us look at the following page to understand this. Okay, so on this page you can see specific heat capacity. Just now we already understand the relationship. Thermal capacity equal to mass time specific heat capacity. So now we want to understand in details what is specific heat capacity. So you see the first point. The specific heat capacity of a substance is the amount of thermal energy required to raise the temperature of 1 kg of that substance by 1 degree Celsius. So from here, you understand this 1 kg as the extra point, is the extra point compared to thermal capacity just now. Thermal capacity is amount of thermal energy required to raise the temperature of the substance by 1 degree Celsius without specifying 1 kg. But specific heat capacity has this 1 kg as the extra point. So this overcomes the weakness of thermal capacity that I'm trying to mention just now, where I said the 1 kg copper and the 2 kg copper has different thermal capacity. 2 kg copper will have a higher thermal capacity. 1 kg copper will have a lower thermal capacity. So the mass is affecting here. So specific heat capacity, right? They're set already. Must be 1 kg. Okay, must be 1 kg. Because of that, we have to take it in this way. If the substance is the same element or same things, so they should have the same specific heat capacity. Okay, so different substance, we have different specific heat capacity. So same substance, same specific heat capacity, because the definition has set it to 1 kg. Okay, now let's see the next point. Specific heat capacity has units of joule per kilogram per degree Celsius. So you can see the unit is also different. Just now thermal capacity is joule per degree Celsius. Now it is joule per kg per degree Celsius. So there is an extra per kg over there. So note, different substances have different specific heat capacities. So this is what I'm trying to say just now also. Okay, same substance, same specific heat capacity, but different substance, different specific heat capacity. So from the definitions of specific heat capacity, it follows that if you have more than 1 kg of a material, you will need more thermal energy. You will need more thermal energy. Okay, so let's say if you have 2 kg, so how to find out the amount of thermal energy required? If you have 2 kg, you just take mass time specific heat capacity. Then you get the amount of heat required to increase the temperature by 1 degree Celsius. So again, when you see this, then you should think of, oh, this is thermal capacity formula, which is true. Thermal capacity, mass time specific heat capacity. So likewise, if you want to raise its temperature by more than 1 degree Celsius, you will also need to add more thermal energy. So if you want to raise an object by 2 degrees Celsius, so you should expect the energy required to be more, to be double compared to 1 degree Celsius. So of course, because of all this, we should have a formula to do calculation. The amount of thermal energy required is given by the equation. Okay, so this is the equation. Change in energy, delta E, equal to mass, the M, times specific heat capacity, the C, times change in temperature, the delta T. So delta E equal to MC delta T. Okay, so this is the formula. The formula for the calculation that involve different mass, the calculation that involves different temperature. So we can use this formula, and we need to know the specific heat capacity of the substance. Okay, now let's see more information on this formula. Note that in the above equation, delta E is the change in internal energy. It's the change in internal energy. So if you are wondering what is internal energy, so it is what we discussed before. It is the addition of kinetic energy plus the potential energy of the particle. Ke plus Pe of the particles. Okay, Ke plus Pe of the particles. Ke is how fast the particle move. Pe is related to the intermolecular forces of the particles, and hence when they have chemical bonds that link to each other, it affects the distance between the particles. So Pe is also related to the distance between the particles. So these two are the two energies, which are collectively known as internal energy. Okay, so you see, just now in my explanation at the beginning of the lesson, I said the thermal energy is used in two ways. The first one is increase the kinetic energy, and the effect is temperature increase. The second one is break the bond. Break the bond, then temperature is the same. So since now they talk about internal energy, so it's good to take it in this way. When thermal energy is supplied, so the substance can use it to increase the kinetic energy. The substance can use it to break the bond. Break the bond means increase the potential energy. Okay, so you have to take it in these two particular ways. Increase the kinetic energy, temperature increase. If you are increasing the potential energy, what happens is you are breaking the bond. Melting process happening or boiling process happening. At that time, temperature is the same. Okay, now that is internal energy and their relationship with melting point, relationship with the breaking of the bond, relationship with temperature. So I'm trying to make it clear now. So now next point, C is used to mean the specific heat capacity of the substance. is given. Okay, this is given. So delta T is used to mean the change in the temperature. The symbol delta in math is used to denote a change in value. Okay, so we have two formulas so far. Okay, we have two formulas so far. Okay, now we have done the 2 pages here involving formula. Okay, so just now we have done thermal capacity and specific heat capacity. Now let's continue with latent heat. Okay, so latent heat, the latent heat of fusions is the amount of energy needed to melt 1 kg of a substance. Okay, so latent heat of fusion is related to melting a 1 kg substance. The latent heat of vaporization is the amount of energy needed to boil 1 kg of a substance. So this is boiling. Okay, so when you compare to specific heat capacity just now, that is to increase 1 kg of a substance by 1 degree Celsius. And let's try to relate everything in this way. So you try to look at the graph. Let's say you have a temperature versus the time. You are heating up the substance from solid and you heat it until it melts. So when it melts, the temperature remains the same. Then you continue to, after melting, the temperature continue to increase. After that, it becomes flat again. This should be something that kind of famous. This graph is kind of famous. Maybe you heard before also. So now during this horizontal part of the line, so what happened is the liquid boils. So the liquid boils, and then at the end, when it finishes boiling, it becomes gas. The gas increase in temperature. Okay, so solid plus liquid plus gas, and then gas. Okay, so I call this 1, 2, 3, 4, 5. Okay, so in number 1, the solid heat up. So what happened is increase in kinetic energy and hence increase in temperature. So that means the solid use the thermal energy to increase the kinetic energy, and hence temperature increase. And formula delta E equal to mc delta T. So for the first part, we use this formula because it involves change in temperature. We use specific heat capacity. Number two is the substance use the thermal energy supplied to increase the potential energy or to break the bond. And temperature is the same. What happened here? Melting. So during melting, we don't use delta E equal to mc delta T anymore because there is no change in temperature. We use latent heat of fusion. Latent heat of fusion, what is the formula? The formula is here. LF, latent heat of fusion, equal to energy over mass. LV means latent heat of vaporization. So it's also equal to E over M. So this one means LF or LV, any of this. it doesn't mean divide. It doesn't mean LF over LV. No, it's just LF or LV equal to E over N. So if I rearrange the equation, E equal to ML. The L can be LF or LV. So after that, let's continue with what we discussed just now. Number 2, we use E equal to ML. E, or delta E. E or delta E, that's fine. Delta E equal to ML. The L here is latent heat of fusion. So that's the formula to be used in number 2. In number 3 is where the liquid finish melting and now the liquid heat up. So what happens is the liquid use the energy to increase the kinetic energy, and hence its temperature increase. And because of the change in temperature, so we have to use delta E equal to MC delta T. Number 4, the liquid reach the boiling point, start to boil. So the liquid use the thermal energy supplied to increase its potential energy, or in other words, it use it to break the bonds. That's why during boiling, the temperature is the same. This is boiling. And because of no change in temperature, we cannot use delta E equal to MC delta T anymore, but we use E equal to ML. But the L is LV, latent heat of vaporization. So we use delta E equal to MLV. Okay, and then number 5. Number 5 is where the boiling process finish and then the gas is getting hot, continue to be heated up, and it's getting higher and higher in temperature. So that means the gas use the energy to increase the kinetic energy, and hence its temperature increase. And because there is change in temperature, we use delta E equal to MC delta T. So from here you can see different situations, we use different formula in calculations. Okay, so this part we have done already, and we have to practice, of course. But before we practice, we still have one more part, condensation and solidification. And after that, it comes to the next part where we will do it next time. Okay, so for now, let's finish up this part also. Condensation and solidification. Condensation is when a gas turns back into a liquid. So when a gas is cold, the particle lose energy. They move more and move more slowly. Okay, so let's focus on this. The particle lose energy. They move more and more slowly. So when you see this, you have to understand that the energy here is the kinetic energy. Kinetic energy, they lose kinetic energy. No kinetic energy, then they move slower and slower. Okay, so the decrease in kinetic energy causes decrease in temperature, causes particles to move slower. Okay, then let's continue. When they bump into each other, they do not have enough energy to bounce away again, so they stay close together and a liquid forms. So this particular part I put in blue color. Okay, so it seems like they are talking about the condensations. okay, the condensation. So here I'm going to put it in this way. It is where they form intermolecular forces and then it becomes liquid. Okay, so I'm going to use energy to express this also. You know, we talk about energy a lot here. Kinetic energy, potential energy. Potential energy is the increase of potential energy is to break the bond. So now in the other way around, the decrease of the potential energy is the formation of the bond. Okay, so I'm going to put it here. Decrease of potential energy, formation of bond. Temperature is the same. This happens during condensation. Beside condensations, you know, boiling, melting, right? Now the other way around, condensation and freezing or solidification. So I will not use solidification. Solidification means freezing. Okay, so that is what happens here. So I put it in the aspect of energy. So decrease in kinetic energy, temperature drop, particle move slower. Okay, so when you see this, you should think of the graph in this way. Temperature and time. The gas decrease in energy, condense, then drop again. That is where after condensation it becomes liquid, right? So the liquid drop in temperature, and then freezing happen, and then it becomes solid drop in temperature. So it is the other way around compared to the previous graph just now. So where this is, if you compare with just now, so this is gas plus liquid plus solid. So this is 1, 2, 3, 4, 5. Okay, so we can put it in the same way but in opposite. So where number 1, decrease in kinetic energy, temperature drop. What formula? This formula. Number 2, condensation, decrease in potential energy, formations of bond, same temperature. What process? Condensation. Formula: delta E equal to ml vaporization, because this is gas. Gas is there, vaporization. Number 3, liquid drop in temperature. So decrease in Ke, decrease of temperature. Formula: delta E equal to mc delta T. Number 4, this is where solidification happens. Decrease in potential energy, formations of bond. Temperature is the same. Process: solidification. Formula: delta E equal to ml fusion. This one. Number 5, solid drop in temperatures. Decrease in kinetic energy, temperature decrease. Formula: delta E equal to mc delta T. Okay, so it's just the other way around. Now we look at the last point. When a liquid cools, the particles slow down even more. So here, number 3, liquid slow down even more. Eventually they stop moving except for vibration. That means solidification happens. Then it stops moving. It just vibrates. Okay, so that is where lose in kinetic energy, right? So just vibrate. Okay, so we have done until here, and let's practice questions. State what is meant by the specific heat capacity of a substance. So this one you have to memorize it. Okay, so here we take it as discussion straight away. So this is defined as the energy required to increase temperature of 1 kg of a substance by 1 degree Celsius. Okay, so 1 kg 1 degree Celsius, 2 marks. Okay, now we look at B. A student carries out an experiment to find the specific heat capacity of aluminium. Okay, so he uses an electric heater and thermometer insert into separate holes in an aluminium block. The following data are obtained: mass of aluminium 2, power 24420, time of heating 95. So of course, when I give you power and time, you should think of energy delta E equal to power P multiplied with time T. So you have to think of this, delta E equal to PT. Initial temperature 19.5, final temperature 40.5. So you use these two information to find delta T. Delta T is 40.5 minus 19.5, so which is 21. Calculate the values of the specific heat capacity of aluminium given by this experiment. So the formula, delta E equal to MC delta T. So of course, if you are not used to this version, sometimes you may also see E equal to MC theta also. So or any other similar form will be just fine. Okay, now delta E is power times time. So 420 times 95. So the M 2.0 kg, the C unknown, the delta T 21. Okay, now C equal to 420 times 95. 420 times 95. Okay, let's press with calculator. 420 times 95, 39900. Okay, so we have 39900 divided by 2 times 21, 42. Okay, so we have 39900 divided by 42. Okay, so we get 950. 950. So from here you will realize something. They don't tell you the unit. You must put the units on your own. Joule, kg -1, degree Celsius -1. If you don't want this way, you can also put joule per kg degree Celsius. Can also. This is the second way to express the unit. So 950 joule kg -1 degree Celsius -1. Okay, so That is how we use the specific heat capacity formula. Okay.